Today I'll be going over a presentation titled Speed, Space, and Scale, TidesDB and MariaDB. I'm Alex, the creator of TidesDB and the chief architect at TidesDB Corp. Let's get started. 1 second there. So what is TidesDB? TidesDB is a storage engine. So it's a library that you can use to build database systems. It's transactional, it's ACID compliant, and it's built on the idea of a log structured merge tree. So it being a log structured merge tree, its operations are mostly sequential. So writes, deletes, updates, they're sequential, they're appended. So there's no write in place, like let's say a B tree where you have to go update a key. And that update is done in place. With an LSM tree, updates are appended into a log and written to a in-memory, usually sorted data structure, in this case, and a skip list. And yeah, so very fast for modern disk like Flash. TidesDB is designed in a way where we're using CPU level instructions, like atomic instructions, as opposed to traditional locking. We try to minimize the locking in the system. And yeah, we're designed for modern hardware, right? So the hardware of today, pushing parallelism, a large memory, Flash, NVMe, and yeah. So this little diagram here shows a little LSM tree, a hierarchical LSM tree with multiple levels. In TidesDB, the tree is adaptive. So we start at one level and capacities adjust. Levels grow from 1 through to n and can shrink as your data changes within the tree. When I say memtable, in TidesDB is a skip list and a write-ahead log. So we'll get into that. As you can see on the right diagram there, we have L0, L1, etc. L0 is normally unsorted files, so logs so the memtable has the associated. So the memtable has a skip list and a write-ahead log, and the write-ahead log is its own file that is L0, right? So L0 can have many. It can have a log, an active memtable, and then immutable memtables, which we'll get into. So as you can see on the left side, we have the L0, right, being 64 megabytes. So that is the write buffer size, right? So whatever you set that to, each level grows exponentially. But in TidesDB, this is adaptive, so level capacities they can change as compaction goes forth, and we'll discuss that. So in TidesDB, we have an idea of column families. The column families are essentially isolated namespaces, key value stores. Each column family has its own LSM tree. And in some cases, you can have the non-unified mode, which is the default, and then you can have the unified memtable. So unified memtable uses demuxing and prefixes. So when we write keys into the memtable, they have an associated column family prefix. And on a sorted run, on a flush to disk, which we'll also discuss shortly, which takes a unsorted file from L0 and the in-memory skip list and traverses it and creates a file in L1. But yeah, so you can have the unified and non-unified depending on how many column families you have, right? So we'll talk about the life cycle of a write. How does a write go through the LSM tree, through the storage engine? So TidesDB is, again, transactional. So when you begin a transaction, you can choose one of the 5 isolation levels for read uncommitted, read committed, repeatable read, snapshot, and serializable. A transaction can span multiple column families, atomic, all or nothing. So when you do a write into TidesDB through a transaction and on commit, it's going to hit the memtable. When we hit the memtable, it's going to be written into a write-ahead log and then written into the skip list. When the system reaches in the active mem table, the write buffer size reaches capacity. So let's say 64 megabytes. The skip list fills up to that amount. It's the mem table is made immutable, and at that point it's enqueued into a flush queue. And reads can still access the L0 queue, which will have all the immutable mem tables. So once the mem table is inside of the queue, at that point there we have different workers, and we have a flush worker. So the flush worker will dequeue work, and you can have many flush workers. Flush worker will dequeue work for all the column families, and then at that point traverse the in-memory skip list and create an SS table in L1. An SS table in TidesDB has a klog and a vlog, which we'll discuss shortly. It's also an immutable file. That's the immutable files that are made when the sorted run is occurring on disk. Okay. So when we're doing these sorted runs to disk, when we're doing these flushes to disk to L1, these files can accumulate. And when you have to read from TidesDB through a transaction, it's going to read through multiple sources. So it's going to obviously read through the active mem table, and then the immutable mem tables, and then start to go through L1, right? So the immutable mem tables would be L0, and then you have L1 with the SS table files. So, when looking for a key, we have different ways to obviously speed that up, but we have this phenomenon called read amplification and write amplification. So to assist with this phenomenon, we have the LSM tree has this idea of compaction, right? And compaction, it basically throws away superseded versions and deletes tombstones, right? And reclaim space where applicable. And yeah, so we'll get into how that looks like here. And so in TidesDB, you don't have any set policy like in other LSM trees, like RocksDB, LevelDB, or Cassandra, let's say. In TidesDB, we go by a specific paper titled Spooky, which comes out of University of Toronto. So the LSM tree picks its policy on the go, depending on the state of the LSM tree in a column family. So as I said, each column family can have its own LSM tree, and compactions occur within a column family. Compactions are triggered, and then they're enqueued for work, and then we have compaction workers in which deal with that. Compactions also, they can run in parallel, and we have this idea of sub-compactions, which is out of the scope of this presentation. But yeah, compaction is granular, adaptive, and selective. So it's determined on the state of the column family's tree at that time, and it's highly configurable, right? You can even add triggers for like tombstone state of SS tables, the density of them. So something to dive into and look into. Very interesting. But yeah, let's go into the next slide here. So because TidesDB is primarily uses a lot of atomic operations, so we're not using a lot of locks. So on parallel writes or batched writes, the system can ingest data very fast. And in some cases, depending on how you configure the system, like your L0Q, your L1 file count, the system will gradually start to apply breaks. So on each commit, you'll have a little bit of a break applied if the system needs to catch up on flushes or compaction, or let's say the system state is reaching your configured max memory. So the system has a lot of safety built in. So always monitoring memory and different things, right? So this also applies into the graduated back pressure, and so yeah, the system will slowly start to apply the brakes when it needs to, and cool feature. Let's go to the next slide here. So let's talk a little bit about the reads. So as I mentioned, each SS table file or SS table files in TidesDB, they're paired with like an SS table is paired with two files, a klog and a vlog. The klog is essentially fixed 64 kilobyte blocks or nodes, depending on the layout, B tree or block layout, and the vlog is a self-describing, so each block can be different size in the vlog files. So when a sorted run occurs and a flush occurs, the system in a thread is going to either write the block layout, or you can have a B tree layout, and in the block layout, each 64 kilobyte block can have like a min and max prefix range inside of each block, 64 kilobyte block. And what this allows for is block indexes, right? So each 64 kilobyte block has this min and max prefix range, and the block indexes, we keep track of that. And then when we do a search, when we do a point lookup or a get or a seek through an iterator, we can go to that prefix range on that offset using a block index. But for memory constrained environments, we have this B tree layout as well for the klog. So it doesn't need block indexes. So it's depending on how you configure it. But yeah, on a read, as I stated, we're going to read through the active mem table, looking for the latest version of a key, and then the immutable mem tables, and then look at L1. And we're going to check the latest SS table and the boundaries, the minimax, and see which SS tables we're going to try to narrow down the SS tables to look at. But once we kind of know which SS tables to look at, we're then gonna utilize the Bloom filter, and the Bloom filter is going to say, is this key inside of this SS table, right? If not, then we're going to skip that SS table, right? But if it does exist, then we're going to use the block index. We're going to try, or the B tree, we're going to get to that block. We're going to figure out which block we're supposed to go to. And then we're going to essentially check the clock cache, right? The block cache, we have the block cache, which has this clock eviction algorithm, which keeps decompressed blocks or nodes inside of it. And we'll check the cache. If the block or the node exists in there, we'll read it from the cache. If not, we'll have to do a miss and then read from disk, right? So I don't think I missed anything here. But each SS table has a Bloom filter. Each SS table has its own index, and they can be configured in different ways. And during this process as well, there's something called a manifest, which we'll look at shortly, I guess, in the next slide here. Okay, yeah. So optionally in TidesDB, we have this object store feature, and the object store feature is unique in that it allows for essentially replication. And what's interesting is that everything lives within the object store, and the primary and the replicas essentially like the bucket is gospel, right? So a primary will essentially mirror the bucket will essentially mirror what's on a primary. So you can configure the system to, on every commit, to sync the wall, the write ahead log to the bucket, or like per bytes, or you can configure the sync in different ways. But you also see these different files here, like the manifest and the unimap. So the manifest is like the layout of the LSM tree for each column family. In the case of unified mode, in this diagram here, it's a little bit weird, but the unimap is essentially a mapping for what index number goes to what column family. The manifest files are essentially a mapping of the SS tables at the time for the LSM tree in each column family. And then we have the SS table files in the bucket as well. And yeah, so as stated, the primary, the bucket mirrors the primary, and then the replica essentially pulls the bucket, right? That's the idea here in this one image. So in this object store mode, you can visualize that there's like this idea of tiers. So obviously the mem table and the block caching on the primary or the replica, and the local SS table files in which are opened. the cold, in which you have the local files in which are closed, depending on your open file descriptor limits. And then you have the frozen tier, which is like the files that live on object store. So this applies to the primary and replicas. So in this slide here, what you'll see is that first in the left diagram, you'll see like a read can occur, and it essentially if it doesn't find the data it's looking for inside of the local environment, then it'll do like a read onto the bucket, right? Because we have a uh, a mapping of like what the LSM tree looks like from the manifest, we can easily still go read from the bucket and read, like, let's say a file that is not yet on disk, and do, like, let's say a point lookup will read that specific block or that specific node offset off of the bucket, off of object store, and then read it. Or depending on the operation, we'll have to parallel download SS tables onto the local disk and then continue it from there. So as you can see on the right slide, if a compaction occurs, we will have to parallel download the files and then do the compaction and then modify the object store, removing the older files and uploading the new file. And after that, obviously updating the manifest files on the bucket, right? So it's a dance there. So we'll talk about the failover and how the replication works a little bit. So when you have a local primary and then you have n replicas, right? So the local primary is always syncing to the bucket, depending on how you configure it. You can configure it for very, very durable, not so durable, mid durability, right? You can configure that. If that local primary goes down, depending on how you have this configured in K8, a replica takes over as the primary, and then the previous local primary becomes a replica, right? It's going to resync with the bucket because the bucket is like the truth, right? And then it's going to become a replica, and then you have a new primary. So that's kind of how that works. Very simple, and yeah, that's a high level. Now, with TidesDB, we have the SQL implementation, which is a storage engine plugin for MariaDB called TidesSQL. It's very, very simple. You install it, and you do engine TidesDB. The mapping here is a table, an index, column family. And yeah, you get the capabilities of ACID transactions, stuff from the TidesDB storage engine into the plugin TidesSQL. TidesSQL has a whole bunch of different features, from secondary indexes to vector search, going off of what's inside of MariaDB already. Geospatial full text search with a BM25, time to live, and a lot of cool different features to dive into there. So when it comes to replication and failover in TidesSQL, again, now depending on how you configure it, but essentially when there's like an alter table or a create table or a schema change, this is synced to the bucket, and again the replicas pull that, and the same former stuff applies from that point. Now this is some tproc HammerDB analysis here. As you can see, TidesDB is really pulling ahead inside of analysis, in certain analysis where data does not fit in cache. TidesDB really performs well in that regard. When data can fit in cache, NoDB tends to perform really well on reads. So this is 100 warehouse analysis, but you can find a lot more on the website there. On the next slide here, this is some sysbench analysis, and as you can see, this is where an LSM tree really shows its strength, right? On this kind of a workload where there's a lot of updates, a lot of deletes, a lot of writes. because of the sequential nature of TidesDB being an LSM tree, it's just naturally going to be a lot faster than InnoDB, where it has to update in place, right? And yeah, there's always when to reach for a tool. TidesDB is uh, uh, obviously more write friendly than read. So write heavy OLTP. Or if your data set is larger than RAM, TidesDB is a good choice. Yeah, if you want to have a cloud native backed very large storage, TidesDB is a good for that. And InnoDB is very good for reads, right? It's very strong for reads. It's been around for a while. And another piece is foreign keys. TideSQL it doesn't have foreign keys, but yeah, it really depends on what you're doing. So read into that and compare the two and run your own benchmarks and all that jazz. But yeah, thank you. And if you have any questions, I'd love to answer them. Thank you.